Now, I will place it here because there are still students out due to drama. They would also probably want to know this. I might send it in an email. Also, the MLC girls are not here. Our photos are going to take place during our physics class tomorrow. It won't take the whole lesson, but I will escort you down to the ref. You'll get your portrait photos and then you will come back. Which means your validation for your incline will be done on Thursday. So you need to make sure that you have tabulated your data and you have plotted your graph of acceleration versus sine theta. Yes?
Is it due tomorrow?
The photos are tomorrow. The validation.
Sorry, you said the validation's on Thursday.
On Thursday.
It's due Thursday.
Yeah, you bring it in, bring your table and your graph, all the analysis, bring it on Thursday, and you will sit a 20-minute validation component. Since we did acceleration down an incline, it would be fitting that we look at the forces on an incline and figure out what is happening. So, here we go. Let's just give a nice example here of an angle of theta. We have our weight force. Now, I'm going to draw the weight force at the bottom. Something's wrong with my pen, making wobbly lines. I'm going to try and be consistent this year. I'm going to use F subscript G. Trent and Zach, you haven't stopped talking. It's very rude. I don't appreciate it. Then you have, and I'll draw it up here, your normal force. Okay? We're going to ignore friction for now. In your validation, you need to consider friction, but it's not too tricky. Let's say that we have a mass, like so. Now, the normal force, we learnt the other day that the normal force can only act perpendicular to the surface. So obviously, it's going to be acting up 20 degrees forwards. Okay? Now, those theta degrees. Sorry, last year I put 20 there. So it's theta degrees forwards, okay? Now, here's what I need you to appreciate. We'll put a little asterisk here. These are the only forces acting. For now, we're going to ignore friction.
So,
if we wanted to figure out the net force, we could then draw a vector diagram. So there is our normal force, Fn, and there is our weight force, Fg. So I've just gotten rid of the mass, and let's combine these together. Now, you can straight away see that these two forces are not balanced, okay? They will not cancel themselves out. The only way they can cancel is if they were equal and opposite. But as you make an incline, the normal force starts to bend forwards, okay? So, if we were to draw a tail to top diagram, I'm going to draw that force due to gravity here. And you will find that the net force is there. We'll write it as the sum of all forces. Okay? And I'll show you, it's a very simple derivation to figure out how to solve for it. So, I want you to quickly also write the net force, which is sigma F, is not a real force. In fact, there are not many forces that can actually act on an object. We've gone through a few of them. Gravity, the normal force, we can get tension through a rope, we could get the force of friction, we could get the magnetic force, electrical forces, and applied force. So those are the only, there's only 7 real forces that can act on a mass. Okay? And so they can combine and be balanced, or they can combine and be unbalanced. In this scenario, they are unbalanced. That red arrow acting down the incline is not a real force. It is the vector sum of weight and normal. Okay? So we're now going to figure out how much it is. Okay? But before we do that...
Is sum F B the magnetic force, sir?
Yes, B is for magnetic. In year 12 physics, we'll learn that B is for magnetism. I am going to sketch oh, no, we're not. We go a bit smaller. I'm going to sketch a line backwards. And I'm going to call that F gravity. I keep using W, but I'm trying to be consistent. This is the perpendicular component of the weight force. It seems a bit strange, but there is. No, that's F perpendicular of the weight force, which is Fg. Okay, its arrow is pointing this way. So it's strange to think that even though our weight vector is pointing down, we can just make some arbitrary direction and find out the perpendicular component to the surface. There it is there. Now, if this is theta, then that is theta. And so we can, I just want to draw that arrow a bit more neatly so it doesn't look ambiguous. Look at that. We've got the hypotenuse, we want the adjacent, so we could say that that is Fg cos theta. Now, since Fn is equal to negative Fg perpendicular, we have an equation that I need you to recall, and this, we'll put it down here in a box, that the normal force is simply mg cos theta. All right? So the normal force is going to reduce as that angle increases. Imagine if we could increase this angle, the perpendicular component of the weight force starts to reduce, and the normal force is balancing the perpendicular component of the weight force. We can look at it in a few different ways. You could go, let's set our object on a horizontal surface. Well, that would be theta equals 0. If you had an incline of 0 degrees, then in that case, the normal force is just mg cos of 0 is 1. So that's just saying that your normal force is mg. Let's look at it another way. Let's rotate the angle so that it's 90 degrees and place the box there. In this case, the normal force would be mg cos of 90 is 0. So have a think, on a vertical surface, there's no normal force because the weight force isn't pushing into the surface, and so the surface does not need to push out. So if I placed an object on a vertical surface, the surface isn't pushing against it. In this example, I've left it with an angle of theta. And so at that point, we can say that the normal force is mg cos theta. If we know the mass, and we know gravity, and we know the angle, you can figure out this magnitude. Now, there's one arrow that I should really have drawn red. There it is there. That is the unbalanced force. This is called sort of the parallel component of the weight. The parallel component, we'll call that Fg parallel. That's the unbalanced force. There's no vector here that's trying to cancel that red vector. And if you just look at this simple diagram, well, we had the adjacent gave cos. This one is going to be sine theta. And so we've got Fg parallel is mg sine theta. So, there are two, hold on, we're going to go, these are the two equations that you need to memorize. Okay? Does that look weird and green? Yeah, let's go a different. What about orange? Oh, no, we're not doing that. Let's go blue. Where's blue? No, pink. There we go, that looks good. So, if we go back to this diagram, I've now figured out that that has a magnitude of mg cos theta, and the net force, when I add these two together, it's always acting down the incline. So, a couple of things underneath this box. We'll go Okay? It acts parallel. Always parallel. Are you writing this down, Josh?
Yeah, I have it down already, sir.
Let's just go back to my little scribble, which I will ultimately delete. But imagine we have a mass on an incline of 0 degrees. Well, that's just a horizontal surface. We could say that the force acting down the incline is mg sine of 0. Sine of 0 is 0. There is no force acting down the incline. There is no parallel component of the weight force to the incline. So 0, that makes sense. The object is not going to accelerate left or right if you place it on a horizontal surface. Let's go to the other extreme. If I rotate my surface now to 90 degrees, then the parallel component of the weight force is the weight force. So you go, okay, with an incline of angle 90 degrees, the acceleration down the incline is going to be mg sine of 90. What is sine of 90? 1. So the acceleration down the incline is mg. That's just the weight force. All of the weight force will act if you have an incline of 90 degrees. Okay?
Yeah.
So there is a really cool derivation, and I want to show you. Some of the nerdy kids might really enjoy it. We'll go over here, not in syllabus. Let's have a look. Basically, if we have a horizontal line here, and we're going to write mg here, and then I'm going to write in, that's your weight force, and then I'm going to draw in the normal force, which is mg cos theta. We basically want to show that that red arrow x at an angle of theta degrees below the horizontal, if that's theta, then that's theta. Take my word for it. We're going to use the cosine rule. So watch this. Hugo, shh. We know that c squared equals a squared plus b squared minus 2ab cos c. So I can now throw some things in. Now in this case, x squared equals a squared, so we'll just pick a few. That's mg squared plus mg cos theta squared. I'm going to run out of room. Minus 2. A is mg. B is mg cos theta. Cos theta. Let's tidy this up. That's m squared g squared plus m squared g squared cos squared theta minus 2 m squared g squared cos squared theta. That's equal to x squared. And then we can stop there and probably factorise out. You've got 1 m squared g squared cos squared theta minus 2 m squared g squared cos squared theta. So that becomes m squared g squared minus 1 m squared g squared cos squared theta. That's also equal to x squared. And then we can factorise out. That's m squared g squared outside of 1 minus cos squared theta. Bingo, bango, trig identity. There we go. Someone's whispering it.
You didn't know.
Sine squared theta equals 1 minus cos squared theta. Boom. This bad boy here is sine squared theta. Look what comes out. M squared g squared sine squared theta is x squared. So x equals mg sine theta. Look at that. That's lovely. So we just showed box. What box? You put it in a box? So, again, the smart cookies in, you might then be able to prove, well, no, I think it's pretty easy to prove that the angle is theta degrees below the horizontal. That's always going to be parallel to the incline. Okay? So, let us summarise. In summary, the normal force is mg cosine theta. it is always perpendicular to the incline in direction. And then your net force is mg sine theta, and it is always parallel to incline. If we for now, we will just ignore friction. Okay? So those are the two things that I need you to take away from this lesson. The net force simplifies to something very elegant. Okay? Now, you need to consider friction because your practical asks you to, and it already gave you something. But here's what we do. It's a bit of a trick. We resolve those two forces. We know that there is the normal force and the weight force. We could draw them. There, boom, and there, boom. There's your free body diagram, but we're not going to, so don't. We can resolve our forces and assign a convention. And I would like you to assign a convention that up the incline is positive and down the incline is negative. Okay? Tom Dempster, can you close it? Bring me your laptop to the front now. In which case, this forward vector will be mg sine theta. The backwards vector will be the force of friction. Okay? It's a cheat. It's a cop-out. We know that this is not a real force. This is the vector sum of normal and weight. But if we resolve our vectors onto that incline, then friction will oppose the net force. Okay? So, if I place an object on an incline and it's stationary, I can't think of an incline. There's nothing here that I could represent as an incline. Have you got an eraser? Sure. Here we go. Here's an incline. Here's an eraser. Oh, it is stationary. So I can make the cheat that the sum of all forces acting on this eraser are 0. And so if I know m and g and sine theta, I know that the force acting down the incline is mg sine theta. The frictional force must be equal and opposite. Now look what happens as I increase the force acting down the incline. Eventually, you meet the limit of friction. So any angle greater, while it's sliding, this is what was happening with your trolley. While it was sliding, you had mg sine theta combining with a backwards frictional force to produce a net force. And then you're going to figure out what that net force is. Okay? So, assign a convention. Please go up. The incline is positive. Please recall that this is not a real force. It is simply the force parallel to gravity. Okay? So the next thing we're going to go is, and this is appearing in your prac, and I've got to be careful here that I don't actually answer the whole damn practical for you, but on the front you had that the sum of all forces equals ma, which equals mg sine theta plus ff. That's what you've got written on the front of your prac. Okay? What I need you to be aware of is that this mg sine theta is down the incline, that is negative, and then your frictional force is opposing that. It's going to be positive. Now, you need to plot acceleration as a function of sine theta. So we've got our y term there, and we've got our x term there, but it's currently being multiplied by an m. What mathematical operation could we do to get rid of a multiply by m? A divide by m. Wow. So if I divide by m, look at that. We get, oh look, cancely, cancely. I'm not going to go any further because that's going to be giving you 5 marks in the validation. But now you can see we've now got it in the form y equals... No, I'm telling you guys too much. Don't write that down. Scribble out y equals mx plus c. You need to have some independent thought. Okay? So, if you plot y against x, all right, I just need to make sure that you've all seen that so that you know how to get a few marks in the validation. Okay. Because you are expecting, here's the thing, with your experiment, if there was no friction, you would expect no y-intercept, okay? But there might be. Those little trolleys are going to have a little bit of friction and a little bit of air resistance. And so when you're plotting your data, this is where I say all the time, from year 11 onwards, no effort should be made to plot to pass your line of best fit through the origin. Don't even look at the origin. When you get your ruler out and you're lining up your line of best fit, look at the data, put your ruler down, and then draw in your line. And let the chips fall where they may. Wherever your line of best fit crosses, it might be an x-intercept, it might be a positive or a negative y-intercept. You might know that there shouldn't be one. You go, the math says that there should be no y-intercept, it should pass through the origin. But you can't force the line of best fit through the origin because then it might not be the line of best fit. Okay? Okay, now I don't know what's happened with my keyboard, but let's look at some examples. No, I'm still without keyboard. Oh well.
So in the bottom right of your screen, you press the keyboard symbol, that should like get rid of it.
Nah, doesn't. Oh, it does. Thank you. Okay. Let's have a go. Here is a mass, 0.5 kg.
Where is this at?
This is on the next page.
I mean, we're at, like it's on a...
Page 8.
You didn't get the joke, sir.
Frictionless. Okay, so we're not going to draw a backwards arrow. Okay? I still wish for you to assign your convention. Tell your marker that up the incline is positive, down the incline is negative. We'll say that it's travelling S equals 2 meters. We have an angle of 40 degrees. Okay. And we'll start off that it's stationary. Okay. If we wanted a free body diagram, please remember there are two forces currently acting. You've got your weight force and your normal force at an angle of 40 degrees. See, the problem here is sometimes students are tempted to add mg sine theta. If you do that, what you are now doing is doubling the net force, because we know that this vector plus that vector sums to that, and then if you add another one of those, you end up doubling the net force, which is not the correct answer. So again, sometimes teachers, tests and exams will try and trick you to see, are you actually determining the net force? Okay? All right, so here's what I would like you all to do. Let's solve for the following: the net force, the acceleration, the change in velocity, and the final velocity. And I can tell you these are all vectors, and they're obviously all going to be acting down the incline. Okay, they're all fairly simple. So, sum of all forces equals MA equals mg sine theta. Now, remember I did assign a negative. There's a couple of ways you can do this. You could just leave your gravity as negative 9.8. And then the calculator will spit out negative 3.15. But you know that it's acting down the incline. So 3.15 newtons. Okay. Since we now know the net force, there's a little trick here. You could use Newton's second law and go A equals net force over M, which equals mg sine theta over m, and the masses cancel, and you get g sine theta. So for this one, you don't actually need the mass or the net force. You can cancel it out and go, I'll just go negative 9.8 sine 40, and we'll get 6.92, 6.29. Yep. Don't know.
It's 6.299.
Now, delta V. Now, delta V is V take U. Okay. So, really, since U equals 0, delta V is simply going to be V. So we're back to our accelerated motion equations. We don't know the time, but we've got A, we've got U, we've got S, and we want V. Do we have an equation that we could solve for?
V squared equals 2a. V squared equals 2a.
Yep, that's it. So cancel out that one.
V equals 5.12.
Okay. All right. So again, you can't just forget the stuff that you did in topic 1. We're looking at forces, that'll determine the acceleration, and then we can go back and play with all of the Suvat equations from the first 4 weeks. You can find time, you can find velocity, initial velocity, maximum height. You could slide an object up an incline. It's just you've got to figure out what the acceleration is down the incline. Okay? Let's look at a trickier example. So now let's factor in friction. Okay? Sorry, it should be friction full.
Friction less, friction more.
Again, that's the free body diagram. Okay? We now know that friction is acting right 40 degrees up. Normal force is acting up 40 degrees left. And again, don't be tempted to draw in the mg sine theta because it's not a real force. There are only 3 forces acting, and then we make the trick here is that we resolve the normal and the weight so that they act along the incline. State your convention. Up is positive, down is negative. And so now we can say FF is positive, mg sine theta is negative. We've got to do a side mission because we weren't given friction. So now it's the coefficient times the normal force, but now n is no longer mg, it's mg cosine theta, so it's going to be mu s mg cos theta. Mu is the coefficient of static friction, which was covered in yesterday's lesson, which if you weren't here, you watched the YouTube video. And so friction now has a magnitude of 1.95 newtons, right 40 degrees above incline. And since we basically shifted our convention now up the incline, down the incline, sum of all forces equals mg sine theta plus force of friction. That one's negative, that one's positive. No, you're adding them. Here's the thing. Do not ever say that the sum of all forces is that take FF, because this symbol, this Greek symbol, means sum of. All right? So the sum of all forces is force 1 plus force 2 plus ... for as many forces as you have. That's why you have to then force the sign convention. When you're adding them, this will have a negative value because you're telling the marker that down the incline is negative and up the incline is positive. So the mathematics does the work. Yes, Matthew?
Why is the force acting at 80 degrees above 40?
40.
Well, it says above incline.
Oh, so, thank you. I should have said, what should I have written? Thank you, above horizontal. My apologies.
Cool, Gamble.
So, our sum of all forces, 0.5, 9.8, sine 40, and then we'll have a negative in there, plus our 1.95. So that's minus 3.15 plus 1.95.
Can you say?
Okay. And then again, you use Newton's second law. You can find the acceleration. Now at this point, let's just look at that mu naught again, because you can get some really interesting stuff. This is kind of related to the Prac validation, but it goes off on a little bit of a tangent. So I just did a little bit of thinking last year, and I've got it written down here. We go, all right, the force due to gravity parallel plus force of friction, that's mg sine theta plus mu naught mg cos theta, and that's going to equal ma. Okay? So then obviously acceleration is going to be all of that divided by m. So the m's will cancel, and you get a equals g sine theta. Now it should really be a minus because they're in opposing directions. It doesn't really matter, but you get g sine theta minus g mu naught g cos theta, which has a common factor, is g outside of sine theta minus mu cos theta. And you can start looking at, we could solve for this right now. It's 9.8 sine 40 minus what was the coefficient? 0.52 cos 40. That should give you exactly the same answer. For acceleration to be a positive value or greater than 0, this term here must be greater than 0. Therefore, sine theta must be greater than mu cos theta. You can start playing around with all these little equalities. You go, well, if mu naught, so therefore mu naught has to be less than sine theta on cos theta. So no. Tan theta.
That sounds genuine.
All right. So you've just figured out, Mr. Hamdorf, that for an object to start sliding and not remain static, the coefficient needs to be less than the tan of the angle. So boom, if I gave you an angle of 30 degrees, you go tan theta, your coefficient cannot be any bigger than tan of 30, or it would stick. If it was less than tan 30, it would slide.
It's great.
Okay, give me an example. What is tan 30?
0.577.
Right, so if I had a coefficient of static of friction greater than 0.577, the object wouldn't move. If it was less, it would start to slide down. So you can do all of these fun things with mathematics. Now, in the last 7 minutes, I'm going to give you guys a question. Now, do you have... Okay, I didn't give you any... Do we have any spare space anywhere? Any... Back of the booklet. Front of the booklet. Wherever. I want you guys to do a question for yourself rather than just have it handed to you. Somewhere. I haven't decided yet.
Is the cold is mu less than 10 or greater than 10 theta if it slides? Or if it speeds?
If it slides, mu is less. Right?
Okay, let's look at this from a different way. I gave you the path where you found the unbalanced force, then you found the acceleration, then you found the velocity. Let's go backwards. Let's say that an object slid down that path. Now, for me to make this physically correct, I'm going to find out what the frictionless velocity is. It's going to be the square root of 2 times 9.8 sine 35 times 2.4. Without friction, this thing would slide at a certain speed. I'm going to give you a speed less because friction is going to act. So I'm going to say that V was measured to be less than the frictionless 4.8 meters per second down here. It started off stationary. Okay? So you need to go in reverse. You need to find A, which then enables you to find the net force, which then will enable you to find the force of friction. Okay, so it's the reverse order. So I've made this a physically plausible scenario that friction will act up the incline and it will slow it down. So could you please solve for those three values? Again, starting with A, you need Suvat. And none of this has time, so we're not using S equals UT half AT squared. V squared take U squared over 2S.
Is it just on the back of the book?
Somewhere. Write it on your diary.
Did anyone else get really low acceleration? Really low?
Well, have a think. What have we got? 20.
Oh no, sir, it's not. I figured it out.
It's about 25 on
Yeah, no,
5.
it's alright.
Should be about 4.
I made a mistake. That's all. Let's go.
That then enables you to find the net force equal to net A.
It should be negative.
Well, you assign your convention, you assign down the incline as negative.
What's the value for A?
I got negative 1.
Yep, sounds good.
It's 2.8.
Wow.
If V is 4.8 and acceleration V is negative and acceleration is
Well, what is this?
force of friction.
Do you get FF as being 12? I got 8.6. 8.26. Did you calculate the actual total cost? Acceleration cost?
I think we'll get something like that. But anyway.
Acceleration comes from this.
What was your acceleration? 4.8. Cool.
4.8 squared divided by 4.8 equals Just think about it for a second. You absolutely know.
Wait, what? Minus 9.6? Minus 9.6?
Did I do the right maths?
Oh, yes, no, it's 1.64. No, it's just positive 1.64.
Okay.
Boom.